Okay, you guys, today our topic is chemical equations and balancing chemical equations. All right, so why do we have to talk about chemical equations anyway? Okay, well, what I have coming out of this gas jet, and you already saw this in class, is methane, CH4. Okay, so I've got water and I've got dish soap in here. That's why the bubbles aren't popping. Okay, so inside these soap bubbles, I have methane gas. All right, so oh, pretty nice, but you can't really communicate with one another about what just happened here by saying, oh, pretty, warm, right? We need to have something more concrete to communicate this, a concrete way of communicating this to each other. So that is what we are going to talk about today, are chemical equations that represent chemical reactions. And what you just observed here was a chemical reaction. So what is the equation that we use to symbolize, what just happened there? Okay, that's what we need to write on board. Balancing chemical equations. Okay, so chemical equations symbolize what happens during a chemical reaction. So chemical equations symbolize what occurs during a chemical reaction. So it is our way of communicating with each other what just happened. What just happened in that beaker? What just happened with that methane? Okay, so what did happen? Let's write the chemical equation that symbolizes that chemical reaction. Methane, which is a gas, combines with oxygen, or reacts with is a better way of saying it, reacts with oxygen, which is also a gas, to give us products, yields. Carbon dioxide, which is also gas, and water, which is also a gas. So those are little g's, meaning the phase of matter that each of these things are in, or their state, I should say. Okay. Methane reacts with oxygen to yield carbon dioxide and water. That's the way we read this thing. We say that the methane and the oxygen are reactants, and that carbon dioxide and water are the products. Okay, we know that this was a chemical reaction because we formed new stuff. Atoms have been rearranged, haven't been broken down at all, but they've been rearranged, bonds have been broken, new bonds have been formed here in very complex manner, which we'll talk about later. To get rearranged, new bonds formed to make these two products. Do we always make two products? No. Sometimes one product, sometimes more than two products. Okay, but always on the left-hand side of the arrow, these are reactants, right-hand side of the arrow, products. Our reactants are no more. They have been consumed. All bonds, most bonds, some bonds, broken. New bonds formed to form different compounds. The definition of a chemical change, you have formed new compounds. The old compounds are no longer. According to the law of conservation of mass, according to the law of conservation of mass, in a chemical reaction, atoms, and we can make this broader statement, elements, are not created or destroyed. All atoms in the products must be accounted for. In the reactants. A balanced chemical equation accounts for that. A balanced chemical equation accounts for that. So what we are going to do next is not to torture you. What we are going to do next is to take into consideration this thing, the law of conservation of mass. That in a chemical reaction, atoms are not created or destroyed. In nuclear reactions they are, but we're not talking about nuclear reactions here. We're talking about a chemical reaction. And in a chemical reaction, we don't destroy or create atoms. And so let's go back and look at our methane reaction as it stands, as we wrote it. So as it's written here, one molecule of methane reacts with one molecule of oxygen to give us one molecule of carbon dioxide and one molecule of water. Or if we want to think on really big terms, we could say 1 mole of methane reacts with 1 mole of oxygen to give us 1 mole of carbon dioxide and 1 mole of water. Okay, so let's look at this now in terms of accounting. Okay, I've got 1 carbon here in my reactants, so I've got 1 atom of carbon. And great, here is that atom of carbon now in my products. Excellent. So we're 1 for 1 and everything's just fine. But as soon as we get to the hydrogen, everything falls apart. Because I've got 4 atoms of hydrogen in my reactants. And suddenly now, I've got 2. What happened to my other 2 atoms of hydrogen? Did they get destroyed in the chemical reaction? No, they didn't get destroyed in the chemical reaction. Atoms don't get destroyed in chemical reactions. Bonds break and atoms rearrange themselves to form new bonds with other atoms, but nothing gets destroyed. So our picture is not complete. This quantitatively does not tell our story. We have to balance this equation, and then that tells us the reality of what is going on in the reaction. We have to balance this equation, is what I should have said. And so how do we balance this equation? Well, this is how we do it. I'm going to say I've got 1 carbon here, and I've got 1 carbon here, so my carbon is all okay. I've got 4 hydrogens here, and I only have 2 here. I have to make them equal. I have to make this balanced. And so what I'm going to do is I'm going to put a 2 in front of the water. And so now 2 times 2, this 2 means I have 2 of this whole thing. 2 times 2 is 4, and now it matches. So I didn't just get, well, so far, I didn't get just 1 water out of this reaction. I actually got 2 waters out of it, maybe more. Let's see. We're not done balancing yet. So I've got 1 carbon, 1 carbon. I've got 4 hydrogens, 4 hydrogens. I've got 2 oxygens. I've got 2 plus 2, 4. So now what do I have to put right here? I have to put a 2. Okay, so I just didn't have my coefficients correct. My quantities weren't correct in my previous equation. And so, in reality, people, what happened in the real world with that methane is that 1 molecule of methane actually reacted with 2 molecules of oxygen. And out of that, we got 1 molecule of carbon dioxide and 2 molecules of water. Now, I need to check one more time to make sure that this thing is balanced. I didn't do that at the end, and you always have to do it at the end before you're done with the thing. So, I've got 1 carbon, I've got 1 carbon, I've got 4 hydrogens. I have 4, 2 times 2 hydrogens. So you distribute the coefficient to everything that comes after it. I have 4 oxygens, and I have 2 plus 2 more, I have 4. Okay, so I'm good. I'm balanced. This now is not breaking the law of conservation of mass. That is why we balance equations, people, because we need to see quantitatively what is going on. Now, notice, this is a mistake that people just want to make all the time. They want to do this. Well, wouldn't it be easier if instead of saying at this point, instead of putting the 2 in front, because then we wouldn't have to go back and change this, with the 4 hydrogens, couldn't we just, you know, change this thing to H4O? Couldn't I just go ahead and change this subscript? No, never changing subscripts. Is H4O water? No, H4O isn't water. I don't know what H4 is. It's nothing. H4O is nothing. Okay. You cannot change the subscripts, people. These are the molecules that are taking place in the reaction. We change the subscripts, we change what the thing is. We change the identity of the compound, and you can't do that. So the only way that you can balance equations, the only way, is by changing coefficients, changing the numbers in front. Oh, does this take a lot of practice? You're darn right it takes a lot of practice. And, you know, people come up with their methods of making tallies on both sides. You're going to learn with practice how to do this, no matter what the problem is, and we will practice a lot. So I'm going to move the camera back over to this side of the board, and let's do one more together, and then we'll do a lot in class tomorrow, and continue to for the rest of the year. So let's do something ionic. Let's do copper 2 nitrate plus sodium hydroxide. Ooh, I forgot my phases. This is aqueous, AQ. And that means that the copper 2 nitrate, AQ, is dissolved in water. It's an aqueous solution. And we'll talk more about these phase things later. Plus, again, sodium hydroxide. Notice how I'm moving a little space for the coefficient, which is aqueous as well. Okay, so these two are going to react with one another, and we are going to get some copper 2 hydroxide, and it's actually a solid. I don't want to spoil any surprises though, so I'm just going to leave it at that. And sodium nitrate. And then now, I've got nitrate here. I've got nitrate over here. I have a hydroxide here. I have hydroxide here. We could break these things up, people, and think that, okay, let's count the oxygens separately than the hydrogens. But I say, no, 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 no. These are polyatomic ions. We know them. They travel together as a single entity. And so it's actually easier to think about them as being a single entity than to break them down into their component parts. It just makes the balancing situation so much more difficult. So, if you recognize that you've got nitrates on both sides, you've got hydroxides on both sides, don't split them up. Leave them as hydroxides and nitrates and just count them as that. Okay, and so how do I do it, you guys? What do? I start from the left and I just go straight through. So, I've got one copper and I've got one copper. Good. I have 2 nitrates, and I only have 1 nitrate over here, so I'm going to put a 2 in front. I have 1 sodium, and now I have 2 sodiums. So I've got to put a 2 here. Okay, I've got 2 whole hydroxides, and I've got 2 whole hydroxides. Okay, so now, okay, I think I'm done, but I need to go back and look. So I've got 1 copper, 1 copper, 2 whole nitrates, 2 nitrates, 2 sodiums, 2 sodiums, 2 hydroxides, 2 hydroxides. I'm balanced. Who's ready to practice tomorrow? We're done.